Very good morning to all the judges. I'm Chua, and today I'll be discussing about the growth and characterization of zinc oxide nanowire. This is the table of content. Okay, so before I start, the judges heard the news that Malaysia is introducing a new tariff electricity where starting from 1st of July, and society is debating whether the market price will go up or not. But the border of picture is very clear, which is not only Malaysian but a global energy crisis. This is because as population grows, so does demands, urging the needs of sustainable energy. Yet our sun, it delivers 3 times 10 power of 24 joules of energy per year, which is around 10,000 times of the current global consumption. Imagine even we tap even a fraction more efficiently. Thus, I can say that the solar energy has a vast potential in the future. So, in harvesting solar energy, many inventions of solar cells have been made, such as crystalline silicon, thin film, perovskite, and many more. And DSSC, also called dye-synthesized solar cell, which is the topic of my title, it's a type of thin film solar cell. Is created from abundant and inexpensive material, and used in portable electronics and IoT due to its lightweight, thin, and flexible characteristic. The DSSC consists of a light-absorbing dye, an electrolyte, a working electrode, which is a positive, and a counter electrode, which is a negative electrode. While the TiO2, also called tin oxide, acts as a semiconductor in DSSC for transporting electrons. But for your information, zinc oxide can be as an alternative of tin oxide, as its band gap and electron affinity are almost the same. Crucially, zinc oxide offers a much higher electron mobility, which in principle enables faster charge carrier transport and less recombination, while its nanowire structure can provide a direct pathway for electron transfer and significantly faster the electron transit, thus making zinc oxide nanowire an attractive material to be explored in DSSC. However, zinc oxide nanowire and DSSC also possesses challenges that need to be addressed. The main problem that is its efficiency is quite low, which is around 15.2 at maximum, created by Muchiwani at 2005, and other problems like reproducible growth and defect control of zinc oxide nanowire, which is due to the lattice mismatch. Lastly, is the fine-tuning of the electrical and optical of zinc oxide nanowire. Thus, fine-tuning the ratio of aluminium atomic percentage in aluminium zinc oxide nanowire is crucial for achieving the above status and maximizing the performance. Most of the research paper covers 0.5, 1, 2, 3 of atomic percentage of the aluminium, and has found that 1 atomic percentage shows the optimum zinc oxide nanowire properties. Hence, in this research work, the investigation of the aluminium doping will be centered around 1 atomic percentage of aluminium for fine-tuning. The purpose of fine-tuning is to discover a new process-structure relationship and the sweet point for the maximum electrical and optical properties of aluminium-doped zinc oxide nanowire in DSSC. So my title is mainly focused on to synthesize the zinc oxide thin film as a seeding layer using micron sputtering, and to growth and characterization of zinc oxide nanowire as aluminium dope, and lastly to analyze the structure, electrical, and optical properties of aluminium doped zinc oxide nanowire growth on the zinc oxide thin film. So for the scope of study, the intention is to yield zinc oxide nanowire by reviewing up-to-date condition via RF sputtering seed layer, hydrothermal growth, and controlled aluminium doping to achieve vertically aligned nanowire arrays, while characterization of the morphological, electrical, and optical will be done, and the data will be compared to the previous research for further scaling. So, this study is significant as it discovered the existence of a new process, structure, and property relationship by fine-tuning the aluminium percentage. And the research of zinc oxide will have the industrial lessening its dependence on rare material and cutting down the costs, leading to a hand in the transition to a sustainable energy source. So the two is the literature review. So as you can see, this table is summarized the finding of previous research on zinc oxide as an alternative, and found out why nanowire exhibit high electrochemical coupling, and the reason why we choose the hydrothermal as the synthesis method, and it was explained by Chua at 2019. Next. Okay, for the hydrothermal parameter, I also have been reviewed many of the articles and found out that to achieve a vertical aligned zinc oxide nanowire, we need like increasing in growth temperature that will be resulting increase in transmittance and decrease in resistivity by Muchiwani at 2017. And Major Gracia found that 1% of atomic percentage of aluminium has the highest intensity and transmittance compared to other samples like 0.5 atomic percentage and 2 and 3 and of the atomic percentage of aluminium. Other like sputtering parameter, I will be briefly explained during the methodology part. And proceed to the third part, methodology. In depositing the seed layer, radio frequency magnetron sputtering will be used. Firstly, fluorine tin oxide will be sputtered at 80 watts for 1 hour using 30 to 50 nanometer zinc oxide film, and the gas flow will be controlled at around 25 standard cubic centimeter per minute for argon and 1 SCCM for oxygen, and around 1.3 Pascal of pressure will be used to minimize the oxygen vacancy. After that, host handling will be done at 350 degrees in air for 1 hour to improve the crystallinity. Next, hydrothermal growth will be done by mixing hexamethyl tetramine with zinc nitrate hexaderide for equimolar concentration of 0.025 mole, balancing the dye loading with efficiency of charge transport. The mixture is then added with aluminium nitrate monohydrate to yield around 0.9 to 1.2 atomic percentage and put inside the autoclave. The atomic percentage is calculated through the molality of the substance, and the autoclave is then placed in the oven to heat for around 90 degrees and 9 hours. And this is the flowchart of the whole procedure. Okay, firstly, as you can see that first I will sputter my thin film, which is zinc oxide of purity of 99.99 on a FTO substrate, and hope that it will deposit uniformly. And I'll proceed to the next one, which is the hydrothermal, and which is I will use a different atomic percentage of aluminium to dope the zinc oxide nanowire and make sure it grows vertically aligned. And I will characterization it with XRD, SEM, and EDX. And if the sample has a uniform morphology, then I will proceed to the last characterization, which is the optical and electrical characterization. And finally, I can get my results. The uniformity of the thin film will be checked first before proceeding to the hydrothermal, and the XRD, SEM, EDX will be done first before investigating the electrical and optical properties, as the morphology of zinc oxide directly influences properties. Proceeding to the characterization technique, firstly is the SEM, or so-called scanning electron microscope, which is used to verify nanowire alignment, aspect ratio, uniformity, and guide the growth optimization. And next is the energy diffusive X-ray, XRD, which is used to examine presence and distribution of aluminium or other dopants and check purity of the stoichiometry of nanowire. Next is the XRD diffraction, which is used to confirm Wurtzite zinc oxide nanostructure, C-axis alignment, effect of doping on crystal quality. And next is the UV-Vis, or so-called ultraviolet spectroscopy, which is used to record transmittance percentage across the visible wavelength. And lastly is the 4-point probe, which is used to calculate the zinc oxide resistivity. And after that, we can use to calculate the figure of merit for the zinc oxide nanowire thin film. Next, the 34 expected result. So as you can see that the dense forest of vertically aligned nanowire on sputter layer with a diameter of 50 to 100 nanometer uniform spacings, and this cross-section view shows perpendicular growth and consistent alignment. So here's a more detailed view, as you can see. Okay, so next for the XRD analysis. As you can see that the sharp zinc oxide peaks with dominant 002 reflection near 2 theta 34 degrees and have a slight shift for an undot. So it's predicted that from a 0.9 to 1.2 atomic percentage, the shift will be very slightly to be observed. And next for the EDX analysis, as you can see that clear zinc oxide K alpha and oxide K alpha peaks, where the aluminium also have a K alpha peak corresponding to the target and for 0.9 atomic percentage. Next is the UV-vis analysis, or so-called ultraviolet visible spectroscopy, which is used to determine the visible range transmittance. So the up one is the difference between undoped and doped for a coated FTO, and while the bottom one is for the plastic but with a atomic percentage difference of 0.15 to 3%. So for my investigation is a bit similar like the bottom one, but their difference might be slightly. And lastly is the 4-point probe analysis, which is used to examine the resistivity of zinc oxide nanowire, and will be plotted into a figure of merit, which is used to balance between the resistance and the transmittance of the substance. And this is the sum of the reference I've been used in my title. So, as a conclusion, this presentation, it outlines a comprehensive plan to develop a characterization of vertically aligned aluminium doped zinc oxide nanowire to use for as a transparent conductive photoanos in a dye-sensitized solar cell. So by combining RF sputtering of zinc oxide seed layer with low temperature hydrothermal growth and precise tuning of aluminium doping between 0.9 to 1.2 atomic percentage, this study will establish a reproducible synthesis protocol for high-quality zinc oxide nanowire with controlled morphology and alignment. So I will correlate the doping levels with structural XRD, compositional EDX, and optical of UV, vis, and electrical of 4-point probe properties. And I will identify the optimum aluminium concentration, which will be predicted around 1.0 to 1.1%, that maximize the transparency, conductive trade-off as quantified by a peak figure of merit. So achieving these goals will demonstrate the feasibility of a low cost of abundant aluminium doped zinc oxide nanowire, and this insight gain will lay a solid foundation for virtual device fabrications and performance testing, ultimately contributing to more sustainable and scalable solar technology. So that's all for me. Thank you.